Hello, good afternoon. Thank you for staying, which is a point for you. We will start with a short video. It's a video that I received yesterday. We have people who has been recording all along 3 years the making of the project. And out of these hours of film, they have really reduced to the maximum. We have a colleague who has prepared some sentences just to explain the project, but it's there where you see the people who has been really in the field working and driving trucks and mounting the devices in place. It's a very short one, so I invite you to see it. Before we start the afternoon session with the three speakers. So I have to do something? Is it a magic thing? Yeah. Okay, thank you. That's it, 3 years. Some of you, so the images are nice. So, oh, sorry, yeah, I don't have the microphone. So some of you have been there. So the students of the Kiki Nonoji. So most of you have been there. For the ones who have not yet visited, it's a nice place. I mean, normally you go there and it's a sunny day. I don't know when it rains. I've never been there in raining. So we had the pleasure of working in a nice territory and having some technological advantage. So now in the afternoon, we go to the heavy subjects. Dr. Volker Brunner from Kisters will talk about the optimization of the generation and demand forecasting. I like always to talk about Kisters. Kisters is a family company. There's a Mr. Klaus Kisters, which is the current CEO or owner or Führer, the boss, yeah. So this is a company with about 500 people, and most of them, majority of them, engineers, statistics and mathematics, that they do strange things that I don't understand, and Volker will try to explain. So please, for his use.
Well, thank you, Santi. Welcome to the afternoon session. And first of all, I wanted to thank Santi, because no one else does it this day. It's unbelievable. He was the one who brought us all together. He keeps us happy over 3 years. And he taught us how to work together and to motivate us all over 3 years. So thanks a lot. Thank you very much.
A lot of beer.
Okay. So, the next, let's say, 20 minutes, and it's all about forecasting, and we're already late, 10 minutes, so it's all about forecasting. I want to talk about the optimization and generation and the forecasting. And just to give you the motivation behind of that is, first of all, I want to start once again with the concept. What is the concept of the different systems? And then what is about forecasting? What is the global optimization? And last of all, some conclusions. Well, first of all, this was a very easy, very early picture of the presentations we have of a project 3 years ago, but it's still worth to show them. The concept of smart rural grid aims of the operation of local assets in local microgrids, so local to local. And this is either in the so-called normal operation, that is a connected mode, or it is in an island mode, which is something special. And that means that the microgrid itself is totally responsible for balancing the power and the supply of all customers. And this is true as long as we are able to forecast the demand. It's very important to know what we have to deliver. So it's all about integration of, well, for sure renewable energy sources, but also conventional ones. We also have gensets, diesel generators, for example, which we could include as well, and energy storage, and how to use the energy storage capacity in the best way. Well, and one idea could be that each rural region and maybe even every village is self-contained with energy. And in the end, it's we are creating a resilient distribution grid. That's the basic idea. So in the end, to do all of this and to carry this out, we need data. Yeah? Therefore, we need data concerning the load demand from every customer, or we need the PV generation, for example. If there is something like wind turbines, we also need them. We need the state of charge of the batteries which have been applied to the grid, and we need the overall situation of a grid. So is it in a connected mode? Is it in island mode? What about the load flow to the secondary substation? And to do all of this, we need to exchange data which comes from the SCADA system, which is the control center of Esther Bonnell, and exchange the data to the management system. In this case, it's the global management system. This will communicate with the IDPR and with the batteries. So this is even more complex and even more vital in case of an island mode, because in that moment, we have to balance everything. There is no falling back. There is no insurance like a grid in front. Everything has to be balanced. So it's a very good idea to have an idea what is going on the grid, to have a good forecasting. So, okay, forecasting. First question is, do we really need a forecast of every customer? Do we really need a forecast of every asset in the grid? What would be the standard approach? The standard approach would be to use standard load profiles. Yeah? Standard load profile is an average of over thousands or millions of customers and say, okay, in average, this is behavior. Well, for example, this is for true, it's very simple, but over 1 year, this is always the day, this is more or less the behavior of a typical customer. Okay, would it be sufficient? Is that enough to carry out an optimization and carry out the operation of a microgrid? Well, in the end, not really. The reality is something like you see on the right side. So it's totally different shape. In terms of energy, it might even be the same. So the energy over the day or over a week might be the same in the standard load profile, or if you have the distinguished and special and an individual forecast. But in the end, we talk about power. We need the energy and the power at every quarter of an hour. So that's the reason why we have to do individual forecasting all over the day. One example, this is from Rosenheim, 3 years ago, 2014, so it's quite a long time, but it's real data. What you can see is the blue one is the active power, and it's negative. It's negative from the perspective of a transformer. That means it's feeding back into the grid. So over a really sunny day, there's so much photovoltaic installed here that it will feed back. In the night, here the red one is directly behind the blue, so blue is not zero. there is a little consumption, yeah, but overall, well, we have a problem here that it is feeding back. And feeding back photovoltaic, or feeding back renewable energy at all, is often limited by the capability or capacity of the lines, which have often problems with voltage. Having problems with voltage, with a voltage band, means having problems with reactive power. So it's a good idea not only to forecast the active power, but also the reactive power. So that's the reason why in this project we have forecasted both, active and reactive, more or less for every load, more or less for every asset which was in the, or which is in the pilot area. And we have to do it at least for the next 24 hours, which was the aim, in a resolution of 15 minutes, at least 24 hours, because we want to use the whole cycle of a battery. So the overall structure, Ramon showed it this morning, is something like this. We have 4 different layers. On the first one is every single assets, like the generator on the loads. And the second one, if we go back one, we have the IDPR, which we'll hear later on, something like a CHP or a genset or something like that. So something which is controllable, that's the idea. And then we have on the third layer the SCADA system, and finally something like, yeah, let's say a kind of brain over that. It's the fourth layer. You might call it virtual power plant, you might call it however you like, microgrid control system. It's something which gives the set points to the SCADA system. So in the local area, we have a local energy management system, which is, beside all the control over the IDPR, also something like an optimal power flow to balance the phases, the 3 phases. And on the global level, we have the forecasting, optimization, and a kind of basic OPF as well. What is very important, and I think it's David asked this morning, the open structure between the different systems, that there's no level is skipping another one. So it's always a direct communication only with the next level. So the set points which come from the global EMS go to the SCADA system and not directly to the local EMS, because there might be some security issues or whatever, which is only known here. That's the reason why we can use the SCADA system which was inside directly and integrate it into the system. So it's the task of a local EMS to do it per grid cell, looking more or less only to the direct neighbors, to the direct assets left and right, while the global EMS should take the old topology into account. Okay, talking about real data. The forecasting, well, the difference between forecasting, which we are used to for mid-voltage or let's say in urban areas, thousands or millions of customers, here we have a very low number of customers. So let's say at a low voltage level, it's here in the first example, it's the secondary substation of Verger, 16 customers. That's not very much, only 16 of them. This is how they are spread and located. Altogether, we have a peak load about 100 kilowatt or 25 kilowatt ampere active on the reactive side. So the question now is, what is the typical error which we could expect? And a quite common used benchmark for error is the average percentage error, the so-called MAPE. You might find it in Google and in literature. So what was the expectation? Well, first, before we start with it and say, okay, typical urban areas, we do not have something with 16 customers, but let's say 100, 200 customers, something between 3 and 4% is typical error over a day. And well, in the end, 3.3, which was surprisingly good. This is very much data, sorry for that, and it's more for documentation later on if you want to take a look on it. But the bottom line is, it's still quite good, 3.3, let's say 4%. What's even more important than the error is the distribution of the error. So the question is, how typical and how trustful, and how much can we trust into the results which the system generates? And this is, well, more or less symmetric. It's nearly a Gauss distribution, so quite good. believe me, there are other examples, yeah, but it's quite good. So that's the active side, active power side. What about reactive power? Reactive power, the gradients are usually much higher. The volatility is usually much higher, as you can see here in this shape. But it's still, well, it's quite narrow. The band is quite narrow, but it's still reliable. Okay, 20%. That's not perfect, but it's still much better than every standard load profile. Okay, so what about a real challenge? In this case, we have only in words, two customers. So that means no statistical mixing at all. Yeah? If one customer switch on his laptop or off his television, you can see directly. It's a hub of 10 or 15%. Well, as expected, yeah, the error goes up 14%, and you see, okay, that's statistically point of view not really symmetric anymore. It also has a so-called bias. That means there's an overall shift of energy, and it was even worse with the reactive power. But still, it's at least twice as good as a standard load profile. So even in this very extreme situation, it's a good idea to make an individual forecast and not to use standard load profiles. As long as and this is the case here, as long as we need really the values of each customer. Okay, now we have forecast. Okay, we have all the airsets. We know the data coming in. We also do the same for not only for the demand side, but also for the voltaic generation, for example. Next step is to do the optimization. Optimization on global level. That means to take some strategical decisions, what to do the next 24 hours with each asset. How to manage the battery, for example, very important. And therefore, we have to take the topology into account, any kind of restrictions we have, lot of voltage problems, and also if there are some markets when we have to take them into account. We have simulated also local markets. Maybe we can discuss it later on and see how they influence the behavior. Well, the idea is simply to make the best use of all assets. The question is, what is best? So you need any kind of objective function, any kind of mathematical term which say this is better than that. We have done it by saying, okay, first of all, we have to balance active and reactive power, and we have to do it with minimal costs. So costs euro is the objective function here. We can imagine also other things like minimal losses, but most of the time it's the same. So minimizing costs is usually minimizing losses. Yeah, what is the process then of the optimization? Well, this is a typical example. This is only one small microgrid, in this case Verger. I'll show you the total model later on. First of all, we get all the actual data sent by the SCADA system, like active and reactive power, the mode, are we islanded or are we in connected mode, the state of charge of the batteries we have, and also all our own forecasts, so everything which we do ourselves. And next step is to import all the data sent by third-party systems. Well, something like PV generation, forecast, and also, if so, all kind of obligations we have on markets. So something which is already sold, or any contracts we have to simply fulfill. Well, and last but not least, well, the optimization carries out the mathematical process and evaluates all the set points for each individual asset. So for every single asset here, you get a schedule. You get a schedule for P and for Q, for active and reactive power. Well, and this is then exported to the SCADA system. In terms of the pilot project here, a pilot area, it takes about the whole process from starting the import until ending the export. It takes about 30 seconds, so below 1 minute. I think it's fast enough, and that allows us to do this periodically. So update it every 15 minutes, the values. So this is the picture for the old pilot area. Here you see the 4 substations, the secondary substations. You see the switch between them, and it's more or less the same idea. We have 2 balancing nodes every time for reactive and for reactive power. Both have to be balanced, and the grid, or the middle voltage grid, or the market, if you like it from this way of perspective, is here. Okay, so one more example. Ramon already showed this morning some slides regarding battery and the use of battery. So we have here now one more example. In red you see the forecasted, in this case, active load for 1 week. And in green, I think it was green, in original idea, is the photovoltaic generation. So it's not every day the same, and it's not always in perfect Sinus, as you see here, but this is just forecast. And this is the outcome. Here you see the state of charge over 1 week, the schedule for the state of charge. It doesn't have to be the reality, but this is what this optimization systems say. And we already have modeled the losses of a battery. So regarding the state of charge, there are losses, which you can see here in the little sparks here. It's a reloading over the day due to losses. And here you can see what is the remaining part, which is taken from the grid. So this is the rest. This was for 1 week. This is for a day, just to see it a little bit more. And the same as you shown this morning, this is all together. Yeah. Once again, everything, here's the 0 line. Everything which is below is load. This is the active load. Here you see the charging times every time the battery is charged. The peaks over the 0 line are discharging. The photovoltaic and the rest is taken from the grid. Well, and just believe me, the sum is 0. Yeah, if you take everything together, the sum is 0, and that's the task of the system. Okay, so what are the conclusions? First of all, well, it seems to work. It's a very good idea. But there are some business cases behind that. First of all, we see we have an operational system, an operational approach, which might postpone or even avoid invests like new transformers or new lines. That's the overall idea. So postpone or even avoid grid reinforcements to renewables. So we were able to implement more renewables without making a reinforcement of the grid. We're also able to reduce the peak loads by orchestrating all the assets, and that's also an improvement of the power quality. Well, and last but not least, this is an enabler for a local market. Yeah, simply because the batteries, for example, will react to a local price signal. It would be one approach to use them. Well, forecasting, we saw that it is necessary to do a forecasting, and even a bad forecast is better than a standard load profile in this case. We also saw that it is a very good idea to do this on the active and the reactive side, because we need the reactive side for voltage limitations. The question how many active power we can carry over a line. And well, results we have from a pilot phase now, it is now 5 months up and running, are very promising and most of all reliable. That's very, very important. Well, the optimization, in the beginning we asked ourselves, we just wondered, do we really need optimization? It's a small asset, it's a small grid, only 4 or 5 assets. So why an optimization? It's something you can do with Excel more or less. Well, not for 1 week, not in every quarter of an hour. And as soon as batteries comes into the game, as soon as batteries are there, you need an optimization to find the optimal scale over time. So it's the key for the use of local storages, we think. And that means also to use all of renewable energy, not to cut off any renewable energies due to grid restrictions. And it's also that's for the island mode, for the connected mode. And in the island mode, it maximizes the time we can live out of the batteries. That's another very important point. Okay, that's all. I hope I will receive some questions, and thank you.
Yeah, Volker, you will receive some questions for sure. At the end, yeah, after the next two presentations, we will have again a panel where you will be able to make your presentations, your questions, sorry. Now, Mr. Ferran Castro, in the consortium of 8 organizations, 4 of them were Catalan. We have people from Xarxa Oberta, from anything having to do with fiber optics. We had UPC, CCA UPC, they are coming later, and Ferran Castro from ZAB, former DMAT, and currently I don't know the name anymore, because this is one of these companies which is staying, but the name is changing. So please, the floor is yours. With him, the challenge was about distances. Up to. We were lucky. At this point, we were very optimistic at the beginning. And our first proposal said that we would reach 15 kilometers distance with a PLC. And it was then the project officer who said, please write down up to. And this saved our life.
Thank you. You hear me? So, thank you for being here. Thank you to Stavanel for giving us the opportunity of sharing all our knowledge with you. My responsibility in the project was communications, and I will show you a nice picture. This is Google Earth, actually. This is by Fogona de Ripollès. So we have the different substations, Bergerno, Planallonga, Piella, and Artigas. So our purpose in the project was to build a communications network to give support to the IDPR. I mean, communications are never a goal in itself. We pay a service to the telecontrol system. So the question is, do we really need another PLC? Are you sure about that? So let's have a look at the current state of the art. This was an interesting overhead that we showed in Brussels in the beginning of the project. If I draw transmission time and geographical distance, then it happens that I have the early PLC systems, dated 20 years ago, were intended for high-speed internet access, so providing internet access to the home. At that time, the idea was to reach 45 megabits per second, which was notorious. We are talking 20 years ago. 45 megabits per second 20 years ago. That was really challenging at very short distances because they had to cover the distance from the secondary substation to the home. That's hundreds of meters. Then, today we also have PLC for smart metering system. PLC for smart metering means transmission capacity is relatively low. We don't need any more than, let's say, 100 kilobits per second, order of magnitude. And the distance is, again, from the secondary substation to the home, to the meter, in fact. So we are talking about hundreds of meters. We also have PLC for in-home applications. So believe it or not, you have your computer in the dining room, and you have the printer in your sleeping room, and you can communicate them over the mains. So the wiring at home becomes a local area network, and for this, it is said that you need 1 gigabit per second, but at least the house where I live is relatively small. It's only 20 meters from one side to the other. And then we have PLC for energy management. This is one of the technologies which is being taken into account for the electric vehicle. We talked about electric vehicle this morning. It's 1 megabit and again short distances. Now, The rural environment means I need to cover long distances. I'm not talking about hundreds of meters. I'm talking about some kilometers. We focused our mind on 15 kilometers at the beginning of the project. We had some nice discussions with the project officer. She said, don't be so strict with yourself. Just say up to 15 kilometers. So we decided that we would need a PLC system covering this distance, and since we are talking about rural environments, the amount of information is relatively low. I'm going to give you some numbers about the amount of information. So this is why we focused our ideas on new PLC design. Now, this overhead has been borrowed from my colleagues of the UPC. These overheads actually describe the operation of the IDPR. The IDPR is the star of the project. I have to provide communications service to the IDPR. So the customer is always right. Let's look at the customer. And this is what the customer needs. Customer needs this exchange of messages without set points. My colleague Volker has just talked about set points. This with set points, so this exchange of messages, these sizes, and in these periods of time. So if we take the hassle to go over all possibilities, then the conclusion is the worst case is the IDPR will need a message of 512 bits in 10 milliseconds. That is the worst case. And that leads us to 51 kilobits per second. But if you remember Ramon's overheads this morning, the IDPR is connected to an RTU that encapsulates all these messages into a 104 protocol. So we encapsulate this in a 104 protocol, which means TCP and IP, and also looks like a nice idea to prepare the system for the cybersecurity world. It's a fashionable subject these days. So this, if I add this 512 bits, I add the TCP and the IP security, then that leads to a requirement of 166 kilobits per second. And now, we go back to the previous overhead, and you will see, yes, there are 1, 2, 3, 4 substations in Baifogona. So we thought, in the worst case, we might be able to handle up to 4 IDPRs. So we desired a concurrency factor of 4. So if this is valid for 1 IDPR, then this is valid for 4 IDPRs. So to sum up, the specifications for the project are 600 kilobits per second in 15 kilometers until the very first meeting with the project officer. Then the specification became up to 600 kilobits per second up to 15 kilometers. Now, don't get scared about this. There's no exam today, no problem. Now, is this technically feasible? Can I transmit these kilobits per second over such a distance? And the answer is Shannon's limit. Shannon, in 1948, he wrote his PhD thesis. It's only 3 pages, and he proved this expression. This expression gives you the maximum transmission rate that can be attained over a given communications channel. And the nice thing is that Shannon was not an engineer, he was a mathematician. So his conclusion is independent from the technology. It is valid for PLC, it is valid for radio, Ethernet, fiber optics. And in, let's say, 1,000 years' time, fiber optics will be obsolete, will be using human telepathy, but Shannon's limit will still be valid. So, we have to compute for this expression that is transmit power, this is spectral distortion, this is noise. When the channel is flat, this expression can be simplified to this one, and the nice thing is that if we look at these 3 pages, we shall realize that this is only valid when there's an infinite decoding delay, which means the system is not useful in practical terms. So if you want to get very close to this limit, you must be able to accept an infinite decoding delay, which is not practical. So, can I transmit up to 600 kilobits per second in up to 15 kilometers? Let's have a look at this expression. So, preliminary measurements, we went to Bifogona. This is, for example, I put a transmitter at El Verger, I receive at Planayonga, Piella, and Artigues, and I look at the channel distortion. Then this is the signal-to-noise ratio at Verger, and then I perform numerical calculations, and that is the conclusion. The conclusion is that in the very worst case, I can achieve up to 2.3 megabits per second. So, channel capacity is higher than I need. 2.3 megabits per second is higher than 600 kilobits per second. That's clearly a green light for the project. So we started the project. First step, laboratory work, simulations. We chose 2 different approaches, multi-carrier modulations and spread spectrum modulations. So we performed some signal processing simulations with mathematical models. That's a simulation of the spread spectrum transmitter. Sorry. That's a simulation of the spread spectrum receiver. If you are familiar with spread spectrum technology, you will notice these are the detection peaks at the receiver. Just as a curiosity, this modulation is being used in all communications systems that focus on robustness, like, for example, GPS or the Internet of Things. Then we simulated the multi-carrier approach with 256 subcarriers. And then we built the prototype. Once we had a green light from the theory and the simulations were successful, we built the prototype. It's basically one board. You can see here the power amplifier, signal processing with all the CPUs and the modulation and demodulation algorithms, power supply, which is more difficult than it seems. Then we have the Ethernet, the communications port, and so on. Rural project means you have the opportunity of having a nice day in the sun, even if you're working, but you're also in a beautiful landscape. So these are the results, but these are real results in real distribution lines, rural lines. So we tested from short distances to long distances. So we tested a very broad scope of possibilities. For example, short distances. By short distances, we mean some hundreds of meters, from 200 meters to 500 meters. So the first results were very surprising, and it is the fact that the upper part of the frequency spectrum exhibits better propagation characteristics than the lower part of the frequency spectrum. Just the opposite of the urban environment. All PLC systems designed so far are focused for the urban environment. In the rural environment, the behavior is different. When the project started, I was so happy thinking about rural environments. I said to myself, no interferences at all. I mean, we are surrounded by cows, literally speaking, and cows don't browse the internet. So I felt very optimistic about that. I didn't know that cows don't browse the internet, but cows have electric fences around them. You can't imagine how high the level of interference was in the rural environment. It's unbelievable. And these pictures taken by Ramon, this shows what happens when the power supply to the customers is interrupted, no electric fence, and this is what we get when we have the electric fence turned on. So that is something we have to live with. I mean, real operating conditions is supplying electricity to the customer. So that's what we got. Actually, this shows the frequency response of the channel, and the blue plot, not so easily to see, but the blue plot shows the desired signal plus the interference. So we were successful at distances of 8 kilometers and transmission rates of 320 kilobits per second. I must admit that the following test was not so lucky. The following test was 10 kilometers, and we didn't get any signal at all, transmitting here and receiving here. And it seems that there were no interferences here, but it seems that the reason is we had many lines connected in parallel, T-off, what we call in the electric environment. So it's like having a pipe of water with holes. You lose the water. So it's like losing the transmit power in the lines that are connected in parallel. There's not much you can do about that. There's not much you can do about that. I mean, if there's no signal, doesn't matter whether the signal is robust or not. Then we tested 12 kilometers, and again, we came with very nice interfering levels here. Transmission, we must admit, transmission was not successful. So, as a summary, of the different distances that we achieved, 8 kilometers seems to be the maximum, at least in the rural environment, at least with the technology we have developed so far. At 8 kilometers is, let's make a technical joke, it's only 3 dB from what we expected. It's half the value, and that's only 3 dB from what we expected. And other differences of this PLC system, when you test, for example, PLC for smart metering, then you have a building with many neighbors, and each neighbor has a smart meters, and then all PLC systems transporting the information of the smart meter must be able to coexist. But they all cover more or less the same geographical distance. Now, in Baifogona, this is clearly different. We have Berger, then we have Planayonga, Piella, then we have Artigas. The distances are long, so the distances are different. Now, what happens if one of those signals are interfered? And here we borrowed some concepts from the Internet of Things world. The Internet of Things, one of the highlights is that every system can behave as a transmitter, as a receiver, and also as a relay station for the others. So perhaps today I'm not a person, I'm a PLC actually. I'm transmitting to another PLC If tomorrow channel changes and the attenuation is too high, then I will ask another PLC to do a favor for me. I transmit my information to a different PLC, and then he behaves as a relay station to other systems. So that's what we call the MAC layer, and these are the results of the field test of the MAC layer with one PLC system behaving as a relay station for another two. And of course, transmission rate has to be adapted over time because the level of noise changes. I mean, by Shannon, if you remember the expression, we had noise power at the denominator, but if that changes, then Shannon's limit changes. So we must be prepared to adapt the transmission rate just in case the channel noise changes, which may happen if a customer, for example, turns his computer on, like Volker said, or a photovoltaic cell begins working, a difference from day to night, or so on. This is one of the most, it is not the longest line, but it was certainly one of the most difficult lines, because there's a transition from overhead to underground, which means the channel impedance changes, so we get like a reflected power. I mean, for example, this is air, that is the wall. If I throw a tennis ball to the wall, then the tennis ball will come back to me because of the difference. So same happens in telecommunications. When we have an underground to overhead transition, then a very important part of the transmitted power comes back to the transmitter. So these type of lines are very challenging, and we got 1.5 megabits per second sustained. So as a summary, we can say that with the new PLC system we have developed, we can reach up to 8 kilometers, which is not what we expected. We expected 15, but in any case, that's much better than the previous state of the art, which was hundreds of meters, at transmission rates that are well enough for the operation of the IDPR. So the figures outperform the state of the art at the beginning of the project, and we consider that the PLC system is perfectly able to support the operation of the IDPR. During the lunch, I got a question about PLC and internal latency. Internal latency in this system is 4 to 6 milliseconds. If you remember Shannon's limit, I said that the closer to Shannon, the longer the delay. Is that important for your application? I mean, if you're browsing the internet, 10 milliseconds are not important. But if you are telecontrolling energy, 10 milliseconds may be very important. So that's something you must bear in mind. I mean, when you go home tonight and you browse the internet and you read the newspaper, for example, you will not notice whether the internal delay is 10 milliseconds or 100 milliseconds. Actually, in ADSL, it can be as high as 100 or 200 milliseconds. So this system is intended for the transmission of telecontrol signals. That is why we want to keep the transmission rate as low as necessary, not higher than necessary, to avoid increasing this number. So, any question on the PLC now or later? I'll be glad to answer. Thank you.
Will be later. So, Ferran, the teacher that we always would like to have. Huh? Thank you. And now, Dr. Daniel Heredero, Before being doctor, we call him Danny, but, you know, status, please. From CITSEA UPC, they did great work, and he will explain properly, as he has done during these years in any place that we have been together. So let's start.
Okay, thank you very much, Santi. I would like to say, first of all, thanks, but not only thanks to be there, to be here sharing what we have achieved during these 3 years, but also to trust in us to be part of, we can say, the IDPR solution. We are CITSEA, we are a research center that belongs to the Polytechnical University of Catalonia. This means that we are not a company, but in the end we are engineers. We are engineers that believe in trying to find solutions to achieve a better world. And as an example, this morning we have listened something about the B2G. We participated in another project 7 years ago, developing the first B2G unit in Spain that was able to discharge an electrical vehicle to the grid following a CHAdeMO protocol. And now I think that we can be proud to say that we are part of the IDPR solution, as I have said, and hopefully I can say that we have developed part of the 3 first IDPR in the world. So I think that we can be proud of this work. Okay, so from our side, basically I'm going to explain a little bit the technology and some of the functionalities that we have developed to give to the IDPR the capability to follow the needs that is required for the rural area. So again, I am going to be really fast in these 3 first slides. It's only to refresh a little bit what Ramon explained this morning about the pilot area. This is what we have at the beginning of the project. We have a line directly connecting 4 electrical substations, 2 of them in Poland, the other 2 in a building. You have seen the pictures this morning. Then we have conventional transformers, switchgears, and so on. And the system started to change. And after 3 years, apart from other devices, I also want to remark that the IDPR, it's not only the power electronics that I'm going to explain in the next slides. It's a mixed system that integrates different subsystems. But here in the pictures, you can see how the IDPR looks like for the 3 different pilot sections that we have used as use cases for the project. So again, we have to face with a complex situation because we want to reconfigure our electric system. We want to operate it in island or in grid-connected mode, and this will be a challenge point. So first of all, give some ideas of the conceptual device parts. The IDPR should be able to operate in 2 operation modes. One, we have called them slave and master mode. Slave modes means that we are grid-connected, so we are essentially going to compensate harmonic components, balance the system, and manage the power. At the end, we can sum up these 3 items saying that the IDPR is able to route the energy. And later on, we will see how it works. Then we have another operation mode, that is the master operation mode, that basically the IDPR is used to energize the system. So this means that the IDPR is able to restore, to start up the system in case of a blackout, and in this way continue to supply energy to the customers. So first of all, we have to develop a state machine, a really simple state machine, to give the information from the IDPR side and inform all the other part of the system in which operation mode or in which state the IDPR it's working. Then about the power electronics, we decided to adopt a 2-stages power electronics scheme because the IDPR can operate considering that we are going to connect a battery, a storage system, but also without a storage system. In case that we consider that we're going to connect a battery, we want to be as flexible as possible. So this means that we want to connect different technologies, different voltage levels. The first stage is used for boost the voltage. So we will have the required voltage to operate the AC side at the end is the important part. Also to remark that we have adopted a 4-wire AC converter, and this means that we will have the flexibility and the capability to operate each phase independently, and this will give the capability to support any of the different operation or requirements that the ADPR will need. The ADPR is a power electronic device that is connected in series with the substation, and basically it's divided into main parts. One is what we have called the central control cell that basically integrates the main switches, protective devices, pre-charged circuits, and so on. And then we have the current source controlled power cell that is the power electronic itself that includes the power devices, driver circuits, cooling systems, DC links, and so on. The important part, we have developed an IDPR, we have developed power electronics, but thinking that we have to be beyond the state of the art. We cannot use obsolete technology. In that sense, we have thought the design of the IDPR, thinking in efficiency, and to do that, we have used new semiconductors, new materials, and advanced control strategies. Here we have some examples for the cooling system. We have used spare spin fin configuration. In that sense, we can reduce the volume required from 1.5 to 1/4 than the other extruded alternatives, conventional alternatives. We have also included the use of a full silicon carbide commercial 6-pack unit for the semiconductors. This means that we can use high switching frequency, even increasing the efficiency from 5 to 8% in comparison with conventional silicon options, and we can reduce the volume required by a factor of 2 or 3. Also, for example, for interconnecting the IDPR with the electrical system, we need some coupling filters, and to construct and design them, we have adopted also advanced materials that we can reduce the losses, or maintaining the losses, we can reduce the volume. So here we have a picture of how the IDPR looks 2 years ago. This is the first big version. This is for lab. For lab, we need a big device because we need to connect our proofs and so on to test that all is working properly. But to give some figures, this first version is about 35 kilowatts. The size is 700 per 300 and 300.5 millimeters approximately. We have only including an inductive filter of 400 microhenries, a big inductive coupling filter, but this was quite heavy. We are talking about 80 kilos. So we have done work during these years trying to evolve this first version, trying to reduce the size and also enhance the capabilities of the IDPR. In that sense, we have developed the second version. This is the version that currently is installed in the pilot area. We are talking now about 22 kilowatts. This is just one cell, so this only integrates one silicon carbide module, but the size is reduced. We have used a rack-mounted enclosure in order to facilitate the assembly in case that we want to parallelize the system. We have also included not only the inductive filter, but also the capacitive filter. Remember that the IDPR has to work not only connected, but also disconnected. So this means that we need to control the voltage somehow, and to do that, we need a capacity. So in this case, this capacity is also included in the same stack, let's say. we have also developed some extra printed circuit boards also mounted in a rack to include some extra DC link to stabilize the inner DC link of the system in case of necessary. And we have obtained, for the same amount of power, comparing them, a reducing weight of 30 kilos. So for the first iteration, I think that it's quite good. Then splitting the different parts that integrates the power electronics and how it's controlled. Here there are the different components that integrates the IDPR. We have a master control board that has been developed for the project based on a DSP that has embedded two cores. One is a DSP itself that is directly used for the control of the power electronics, and then one ARM that is used just for communications. So we can separate the part of exchanging data with the part of controlling the currents and voltage itself. Then this master control board has also integrated the state machine of the system and manages the set points for the slave control board. Each slave control board, it's able to manage up to 2 cells. One cell is what we can see here on the slide. There are 3 different pictures of the same unit. Then for the 2 units that considers battery, we have included a lithium battery of 320 volts and 60 amps hour. And then here also the extra DC link. So this is just to give some idea of what technology is included in the IDPR, but I also want to show the important part that it's what is capable to do, what is able to do the IDPR. Here we can see 2 different schemes only to represent that we have 2 solutions. One that includes the battery, so we need the 2 power stages that I explained before. One to adapt the voltage at the battery side, and the other one to operate, to interface our IDPR with the grid. And in case that we just use an IDPR without battery, we just need 1 power stage. Well, this is a funny result of the project. We have developed for the project advanced control algorithms, and one of them is that we have formulated a new type of controller. Okay, this is a particular case. This is a lab case. For sure, we cannot inject a Batman in the rural system. Okay, but this is just to show the capabilities of what we have developed. In that sense, we are able to follow really strange waveforms. So this means that we can compensate, we can do almost whatever we want in terms of current or voltage. Okay, real results. These first ones are from the lab, but then we will see a video from the pilot area. The first thing, functional test. We want that the IDPR has the capability to compensate reactive power. So this means that, for example, before we install an IDPR, this green line represents the voltage, this light blue line represents the current. Here we can see that both waveforms are shifted 90 degrees. So after the incorporation of the IDPR is the responsible to inject this reactive power, and this means that the line is discharged from this responsibility. So we are using the current infrastructure to what we need. It's for what it was designed at the beginning, is to transmit active power, not reactive. Then another thing, and this maybe represents in the best way the concept of routing. Imagine that we have a system. These are the 3 line currents. 2 phases are with almost no load, and one is with some current. And the IDPR has the capability to say, okay, I'm going to consume in a balanced way the currents from the line side, from the DSO side, and then I'm going to supply just what I need at the load side. So this means that we are routing the energy. We are, for example, we need 10 amps of current in phase A, but we are consuming from the grid side 3.3 approximately amps per phase. Another example, in grid-connected mode also, we can have an aggregated load that at the end suppose a really nonlinear load. And this is an extreme situation. But for example, imagine that we have a load with this profile that represents about 61% of THD in terms of current. The IDPR is able to supply all the harmonic components except the 50 Hertz component, that this last component is supplied directly by the grid. So the grid sees only less than 1% of distortion, and all the distorted components are supplied by the IDPR. This is all for the grid-connected mode, but what about the grid-disconnected mode? These are also in lab, but for example, in this case, these three waveforms represent the three voltages, and then we connect, in the worst case, just more or less at the peak in terms of current, a heavy load. The IDPR is based on power electronics, so this means that we don't have the inertia, the mechanical inertia that we will have if we are generating with a rotatory machine. So we need to supply that current in a really fast way in terms of voltage, because the load, in other way, will see a dip or a sag depending on if we connect or we disconnect the load. So as you can see here, we are able to support that heavy consumption just with a really fast transient in terms of voltage. So this is good because we are supplying inertia in terms of current. What about nonlinear loads? This is a more extreme case. Then the transient is a little bit longer, but in less than 2 grid cycles, we are able also to support the required voltage to continue feeding the load. One interesting case, it's something moved, but I think that I can explain it. Well, here we have a similar situation, but if we are operating the system in grid disconnected mode, we have also to ensure that in case of a short circuit or an overload, the system will be able to reduce the voltage accordingly to some preconfigured current, because in that sense, the conventional protective elements will be responsible to disconnect the fault. In that sense, for example, before enable some overload control algorithms that we have implemented, we have 230 volts in each phase. So in case of a fault, we are supplying always the fault, but after activating it, the phase, well, it's the green. I think that it's a little bit difficult to see, but there is a reduction in terms of amplitude. We reduce from 230 to 215 volts, and we supply only 41 amps. That was the current that has been pre-configured as an overload or short circuit current. So in that sense, the responsibility is moved to the protective elements, because the IDPR is able to maintain the same behavior expected as a conventional generator. Then I think that this video is quite interesting. Here, this is an oscilloscope video. It's not nice as the ones that we have seen, but I think that it's quite impressive. These are 3 real currents that we have in Berger one day. This part is a zoom in of the top one. Here, these 3 waveforms are current, so you can see that they are really distorted. It contains harmonic components, and well, about reactive you cannot see because there are any voltage plotted, but you can imagine. What I'm going to do now. No va el vídeo. Pues no. Com? No. well, it's a pity because it was a really interesting video, but no baixo. Okay, well, this is some other results, also extracting data from the pilot. For example, here we have the voltages, here we have the currents, and we are enable and disable different capabilities. For example, harmonic current compensation, or some others. In the first case, we have we are compensating the reactive power and balancing, but you can see that even doing these two, enabling these two capabilities is not enough, because if you take a look, the currents are quite ugly. Then if we just compensate the harmonic components, the current waveform is more sinusoidal, but they are unbalanced. And if we combine all the possibilities in grid-connected mode, they are quite sinusoidal. If we analyze a little bit the data, before connecting the IDPR, the initial situation in terms of power factor, it's that one phase is close to 1, but the other ones are far away. After the connection of the IDPR capabilities, each phase is approximately 1, so this is a good result. In terms of harmonic distortion, the first situation before the connection of the IDPR is that we have, in terms of voltage, up to 2.5% of distortion, and in terms of current, about 70. After the connection of the IDPR, we reduce the current distortion to 6.5, and we have also correct a little bit the voltage. So this means to increase the quality of service that we are supplying to the rural consumers. And in terms of balancing, before the connection of the IDPR, we have one phase that it's only contributing in terms of current of about 80%, and after the connection, the system is totally balanced, and each phase is contributing with 1/3 of the total required power. So one thing that I want also to remark is that the IDPR is a flexible solution. We have developed some power electronics that has to be adapted to each one of the different sections that are included in the pilot area. Berger has a transformer of 25 kilowatts, but it's a 230 volts face-to-face system. Planayonga also has a transformer of 25 kilowatts, but it's a conventional 400 face-to-face volts. And Artigas is a more powerful substation. It considers a 100 kilowatt power stage, that is this one of here. And finally, Artigas also consider batteries, and this, in this case, is integrated by four power modules. So at the end, we want to go towards the digital grid, but how the IDPR can contribute to this digitalization? In terms of efficiency, it allows to include forecasting, and we have assumed the usage of leading-edge technologies. In terms of flexibility and coordination, because we can connect the IDPR to different AC, but also DC systems and technology, and also the IDPR, and this is really important, will allow to help the integration of renewable energies to the system. In terms of management, because we can operate the system in grid, but also in grid disconnected mode, and reconfigure the system according to the capabilities at each moment. And finally, in terms of functionalities, the IDPR can help to give some functionalities as can be time shifting, route the energy, as I have shown, short circuit management, harmonic compensation, balancing the phases, dispatching reactive, peak shaving, and so on and so on and so on. Okay, the ADPR, we can say that it's the muscle of the system, but we have the brain. It's a global EMS, also with part of the local EMS, but somehow we need the nerves that will help to transmit the set points, the operation configuration, and so on. And my colleague Ramon will explain this part, that you will see that the SCADA system has all things needed for the integration of all this intelligence and transmit this intelligence to the ADPR itself.
Okay, thank you, Danny. Well, the last part of this presentation is to demonstrate the real level of integration of all the technology. And also, there are some of colleagues that know me. I explained the same example. It was in the 1985. I was 19 years old. I had a university professor that in the first days of class, he explained when you grow, you can enjoy that TV works by cable, not electrical cable, high frequency connectivity, and phones work by wireless. Believe me, I don't understood anything, but nowadays I remember this sentence because the next distribution network is changing. In this project, there are a lot of goals to achieve, and we take some details from the usual electrical workers, because when we introduce technology that we are able to operate in electrical grid, but thinking in the traditional way, we take a lot of care concerning that for the electrical workers, it's very important that not feel that intrusive in their professional life. The ADPR is not nice. It's not. We are not like Elon Musk. Our capability of design is a square box, and yes, we had a red button from in case we have some doubts. We stopped the systems, and the traditional systems is working again. I will explain the integration. The integration we have from the electrical infrastructure. We have forecasting systems. We had a lot of contribution from Tadeusz in the simulated area. The core of the project, IDPR from UPC engineers, telecom systems, and also from CGA is the leader that they are able to integrate all the protocols to achieve the final project. I would like to share with all of you the integration concerning telecommunication, automation, and SCADA, and at the end, I will share the final conclusions and what is our projection opinion. The system is already working. From the last month and a half, we have 3 IDPs working in grid connected. We will enjoy video that is what recorded yesterday late, but it's the last situation that we can share with you. Telecommunication, Ferran explained that we have several hubs, but our telecom engineers, they are managing from our network operation center the real infrastructure. They are managing several point-to-point, routing, radio, PLC device that they have IP address, managing their own seats. This is an example that is the real Our NOC is, the software is SolarWinds. It's the architecture that they are managing from the access from Berger. The router that we have Berger to split the communication in the local secondary substation and the rest of the secondary substation, Planallonga, Nopiella, and Les Artigas. We are managing level 2 and level 3 protocols. If one of these paths, we lose the path, the systems automatically get another via, another port to achieve still communicating. This is statistics. Latency is less than in the wall of the system, less than 20 milliseconds. Not in the internal getting decisions. It's all the wall. This is the real router in Berger. It's a summary of all integration telecommunications systems. We have several statistics. What is the traffic that we are transferred between a device? We have the profile of PLC things, MAC address, statistics, I don't know, 12 megabits per second, and so on. And this is a real, yesterday, Eduard and Jaume Barbany, telecom engineers, that they are operating from the real network operation center. It's Berger. They are getting all information after if we have a problem. Believe me, the system is very stable. We don't have grave problems. And this is the control operation network in Estabanell. This is the whole of the electrical grid. We have several colors. It's the level of the voltage. And this is the integration in our SCADA. Our SCADA is a basic SCADA, and what is the way we will need to adapt our database? We have the device IDPR, and we have the information object address to create the common information model to use the protocol IEC 870 using the standard. We have all information object address. That means Smart Rural Grid is concerning standardization in common information model. Also, Volker explained from the forecasting, if you remember that we have a screen that also is using the common information model that is the base of the new criteria to achieve intelligence in the network. Without this level of the standardization, it's not possible to upgrade this intelligent technology. This is the screen of orthogonal schemes. We have Israel. The values, the power, active power in the transformer side, in the consumption side, from the IDPR. We are collecting information from the distributed generation and the position and the connectivity. And this secondary substation is like my student March, all zero, because they are not in any consumption. And Les Artigas, and we can enjoy the states. These are working in the state 8, that means it's compensating, but in grid-connected way. And this is a video that we can enjoy yesterday afternoon. We can operate IDPR in secondary substation of Berger, and we can show, you can see what is the effect compensating, balancing loads, and so on, if the quality is possible. The worker in the technical that is working, we are compensating. Okay, they will need to lose the balancing of the load, and you can realize that the load, it's not compensating. It's a real interaction in our SCADA system. Okay, it's not balancing, and when I decide to balance again, for example, the loads, harmonics are reactive, it's few level. Right now, it's again balancing. This is one working in the state 8, the frequency, state of the charge of the batteries, and so on. Regarding forecasting systems, our SCADA is generating all the folders in our database. We are writing Every day and every quarterly message we are sending to Germany server, process the information, we collecting in another folder, we sending FTP protocol in local energy management system and get and take the decisions. This is, for example, last day, this is the values, the set points that we are sending from the process from Kister server till local energy management systems and operator reconfigure the features depending the needs. And at the end, the conclusions, technically side, we believe that the dynamic microgrid give the real flexibility. You know that in Europe there are a lot of information, a lot of point of view that we have balancing conditions. We will need to manage the congestion points, but it's between generation, consumption, but never operating the low voltage grid. If you remember, we have several low voltage hardware that we are operating. That means we can reconfigure in this level of the voltage the real connectivity and topology of the grid to ensure the maximum capability in grid connect on island mode to ensure the maximum efficiency to deliver electricity from PV, depending the consumptions. The quasi-grid concept is for us is a new concept and also important because we take care with the environment. We avoiding to cut trees. Society is very welcome because what is the cost to still cutting every 3 years the distance between overhead network with tree. Also is an important cost. Without an overhead network, we will need to pay anything. And we can create electrical grids to manage from the SCO in another concept, in another mentality, not needed to create and to build a new electrical grid. The demand response and the renewable distributed generation reduce logically the losses. If you remember, the losses we can get if the current tends to 0 or the distance between generator and consumptions also tends to 0. If you are managing local generation and storage, the losses, the efficiency of the grid is increasing. This project also brings, we can start from our utility, introduce the intelligent electrical device, because nowadays we are installing things in the secondary substations that they are able to logging with few effort from the workers. That's using because we have sensoring, not with electrical and analog interfaces. We are exchanging with IP address what is each one. And the systems using the common information model is able to detect and to build in the schemes. Such as it has been mentioned before, a smart rural grid, from our point of view, it's real, it's true that able to manage a real flexibility, not sending constraints, managing the traffic light signals. You need to stop the generation. We configure the electrical grid to ensure the congestions in the low voltage grid. In a low scale, but increasing the number of the device, we can increase the number of the congestion points. In the initial outcomes, the project is going, I think in the next month conclude. We are concluding the final details. The first getting of the values, we can get that the improvement of the losses is 3.23% of the grid. That means that IDPR, the efficiency, is very, very interesting. That is not like it's a little similar a transformer, a little bit less. In the generally side, of course, in rural areas, people is not exigent to use electricity, but we are approach the quality of the service in the urban areas like in rural areas. It's very important that this part of the territory can get the same condition. Now, maybe now it's not necessary to achieve, but in the next year we can, getting this quality of the service, we can give new service for another business to install in rural areas. Regarding market, smart rural grid, we can operate, we can manage several model markets, depending, such as mentioned before, depending the variable to introduce in the data model, but it's not the main issue. We can introduce what is the variable we will need to manage. We can introduce, and IDPR and small scale storage. For sure, give environmental benefits because secondary substation buildings really are narrow. The surface is less. We get the maximum profits in the sense that storage, power electronics is not invasive, and it is able to install. Our first enemy is the internal temperature. Is the second part of the technological work that we will need to ensure. But till now, we don't have any communications problem for more 1 month. We don't have any problems. We get the information. We are interacting with Grid. We are ready to start to operate in island mode. And from our side, projection, for sure. The technology developed in the consortium is scalable. We can install in small locations, in big one secondary substation. It's customizable, depending the DSO that they are interested to install. We can adapt the main design, and also can be exploited to any area of topologies, depending. It's not important the level of the voltage, the electrical system. We can introduce large potential for growth and future development. And from our side, we believe that is the beginning in another way to operate electrical grid from the CO side. Thank you very much for all the consortium and all of you.
So now the last speakers, we go for some questions. Last minute, we will try the video from CCA UPC. At the end of everything, before breaking systems, we will try to see whether it's possible or not to see this video. Questions? No questions. So I would say I've got some of them prepared. It was so difficult. Who is Shannon? Shannon is coming. Okay, we're looking for the mother. So Volker, you were talking about business cases and the ability to postpone or avoid reinforcement of the network when there's an abundance of renewable injection. Any example? Besides what we know from this smart rural grid project?
Yeah, for example, there are controllable, adjustable transformers, low voltage transformers already in place. At least in Germany, they are quite often used, but they're much more expensive than the IDPR. So our approach, I think, is much cheaper, much more cost efficiency. Problem maybe behind that is regulatory authority, because we are talking about OPEX and not CAPEX, operational expenses or not capital expenses. Just buying a transformer and saying, okay, for the next 30 years, this is it, and the authority will allow you to put it into the grid fees. That's a simple thing. But every year, to have a new fight with the authorities to say, okay, these are costs, operational costs, which I have due to this approach and due to personal and due to systems, it's another game. I think that's a little problem. But there are already such examples, as you mentioned. Yeah.
Okay. No questions yet? So Daniel, please, from CITSE UPC. The relationship, this morning we were near to the electric car, electric vehicle, electromobility. Do you think that the IDPR can contribute to the penetration or be a solution or a constraint for the penetration of electromobility in rural or in urban scenarios? Huh? Because we have been talking about smart rural grid. This is how things started. Huh? What we have been discovering along these 3 years is that in rural scenario we need 100% of the features of the device, but part of them, so a cheaper device, can be used in any kind of environment, even urban. Huh? So the question is, which impact can this have with the...
Yes, in fact, installing the IDPR at the low voltage site, it's one of the potential benefits of this kind of solution. I mean, for example, in case of, let's say some number, 25 kilowatts of a transformer, and we have the system really congested, maybe because we have 24 kilowatts used, and imagine that you install some charging point at the low voltage site for charging some electrical vehicle. The IDPR can contribute, can support the charging system, for example, integrating the renewable energies, and in that sense, we don't need to invest some money because we need a new infrastructure to support the, let's say, 10 kilowatts of extra power for charging a car. So in that sense, the IDPR, it's the system that can help, can assist to route the energy, but not just for the overhead lines, but also for the integration of the renewables. So for sure, it can help to a better use of the full current infrastructure.
Okay, thank you. Good. Thank you.
Yes, just to see things start. One question. You have been constantly referring to all of it in terms of the needs and exploitation from DSOs. That's it? Is this just for DSOs? So is there any other scenario in which this could be used? I'm thinking of cities, university campuses, technological parks, big areas. Is there any other area in which this could be exploited beyond the passionate world of the DSOs?
Yes, not just for DSOs and neither for secondary substations. The technology, the project is focusing in the rural areas because in the beginning we're looking for the gap that is not usual for another project. We want to get a differential criteria to install. But technology has the potential to install, to manage several consumption in industry, in homes, in low voltage cabinet network, in depending the needs, the flexibility. This is a device that is able to interact for each part of the grid that we have electrical features. This is the concept, but if we take a look from primary substation till smart meter, we can realize that from primary substation we have high level of automation, or let me say intelligence. And after the smart meter deployment, from the border between DSO and customer, we have a huge quantity of information. But between primary substation till the customers, DSOs doesn't have anything. Secondary substation is the next evolution from primary substation, and the next one is low voltage. And in another side of the meter, of course, is the potential.
But who's going to pay for the IDPR? Yeah, DSO could be, but or an aggregator, or the owner of a local energy community. So at this moment, there are some new figures in the system which are opening possibilities to this technology. But according to the current regulation in Europe, because we have to think in Europe where it's our nearest market, and then we have Africa, and we have India, and we have South America, places where there's no regulation. The need exists, but there's no regulation, so no problem at all. Well, it's only when we are looking at our neighbor markets, so normally speaking, we should expect that the next market will be at home, in Germany, but as we know in Germany, they will be able, a DSO in Germany will be able only to use 50% of the features of the IDPR. So, or other markets, less regulated, or other new figures to make a profit, a business model out of this technology. Because certainly a DSO in Europe cannot have an IDPR in place with the whole features that have been developed.
Yeah, maybe my question goes a bit in line with your last comment, Santi. So I saw on one of the last slides from Ramon, that under technical results, I think you mentioned about 3.3% of less losses. So I've got two questions. So how, if you extrapolate this to bigger areas, do you expect it to, be in that range, or do you expect it to increase? And the second question is, there were kind of a few bullet points that could be expressed in economic figures, euros. Have you taken a look at that aspect as well?
We are optimistic. We don't have enough figures to get, but in the beginning, the theoretical challenge that we wrote in the project, just installing and manage such as we explained, because it's the real outcomes that we can get and share with you. We was surprised because we increased a little bit, 0.17% more. We will need to get more information, more data, and also depending the season of the year, the variability of the loads, the temperature, but at least it's not becoming worse that traditional way. But in euros, right now, I don't have information to share with you.
It's secret. No, the calculation behind the 3.3%, it was, if we talk about local for local, so consumption as close as possible to generation, we get rid of the losses of the transport, the losses of the distribution, and then the losses because the imbalance of phases and temperature and so on. So this is strictly the calculation behind 3%. So if you create more and more micro, it's always 3.3%. But because it was the original estimation. And then concerning costs, we are in there. We are looking for industrial cost, because as far as we have only laboratory prices, even if you scale to 3, 4, 5 units, this is not. There's no possibility of putting this in the market, other than markets with a huge need that we don't know at this moment. But for the needs of an European DSO, we know the limit. This limit we cannot reach. If we go above this limit, then there's no business for this device. Oh no, a difficult question is coming.
Student from UPC. I would like to ask, what is the next step you are thinking of? Is to finding the market where you could monetize this, or finding the business model which you get around and do this business in Europe, or some kind of other technological development which you could apply this in the current constraints?
We have an issue at this moment at developing the business model. So those are students master sustainable engineering from Kikino Energy, and they are helping us. We are learning a lot from them because they have always fresh ideas. And at this moment, we are creating the business model. We will never, ever go for a model which is only based in selling devices. But we are not yet able to describe a service model, which you can establish a long-term relationship with your customers. And now we are in this phase of developing the business models. This is there. Now we are only talking about costs. Okay, cost you can manage. We are producing devices with top range of features that most of the possible customers, they don't need. So we have to look for price. But if we go for a business model based only on selling devices, this is not interesting. This is not a market for 1 million units in the world. So we are looking for a service model based. And we are there. So if you have any proposal, we'll be welcome.
I want to add one comment about business models. We see more and more coming changes, more e-mobility, integrate renewables, local energy markets. So you need a flexible concept to handle this, all these things. So nobody knows what happens in 2 years or in 3 years. And so you have the technology, and now we have to show what we do with it beyond the project now.
Yeah.
I have to say, meanwhile, that last week, Friday, we knew that a new project was accepted. In this project is participating also CCA, UPC, Osfol Innovation Center, and it's led by the Universitat of Girona, and is the son of the Smart Rural Grid. So we have a continuation. We will be approaching the household. We will not jump through the meter. We will stay in the site of the distribution unit operator, but much nearer to the place where the production and the consumption is produced. So at least technically, and so we will have the funds for starting again with a new development. So sorry.
All right. My name is Brent Brendel. Actually, I've been part of this project, but since it's late in the day, I might as well ask my colleagues in the project a question regarding value. Because we heard that the customers or the end users, they are the most important. But if I count the number of references to end users during this conference, I think come to about 5 times. Question is, what kind of value will each of you promote to end users and end users representatives in order to boost the R&D that you have contributed to and create the business models that we're searching for? Because the key is added value.
Thank you. Yeah, again, you have seen in the winter package, they talk about active customers, and this is an existing. So, how many of you read? So you open the invoice with the electricity bill, and you read it. And here, let's say, this, we could consider that this is a quite specialized audience. So unfortunately, and it's our fault. I mean, we, the electrical system, have to recognize that the customer was not important for us until 1 year ago, after 100 years of, because 100 years ago it was about producing, it was about generating huge quantities of energy, transporting and making richness or improvements and social improvements through production and so on. So, and the customer was not relevant at that time. And it's only now, a few years ago, when the system, the electric system, went to the customers and said, dears, you could start playing with demand response. You will like it. You will gain some, or you will save some peanuts, and you will solve my problems of constraints. No? The citizens, the customers say, yeah, we are ready to help you. Now we have the flexibility. Flexibility is when the system says, okay, unfortunately, people has not reacted properly to my needs, so I have to do something, and this something is so-called flexibility, which was the effect of the demand response was flexibility. So at that time, until now, the customers we are making an exercise. There's a town, Tona. In Tona, we have 5,000 customers, 5,000 households, yes. We sent a letter to the 5,000 because we are going to deliver in 1 week time, to deliver them every month a nice document with hourly consumption, some advice, so people can start understanding their behavior and to understand that they can have an impact in the cost of the invoice, just making some minor changes in their behavior. Letter and mails to 5,000, and the municipality supporting us, and so 20 came, which is successful. I mean, could be no one, no? And 20 came, and our expectation is that within 6 months' time, let's say, we can make public that these 20 families are saving money compared to the rest of the people in the municipality. But it's a first step, and my surprise was that when talking with the people from another department of UPC, specialized in big data, they told us that we were going to be the first one in Spain providing this kind of detailed and accurate and positive information to their customers. So nowadays, I don't know, you come from Norway, I don't know if in Norway you expect the customers to say, we want IDPRs in our DCOs, or we will change DSOs. But in Central Europe, South Europe, this will not happen tomorrow. But it's our responsibilities. We are the ones who have to train, to demonstrate that we have to build trust. We have to build trust with our customers. And our customers have to be motivated to be active. If not, it's not that Winter Package will say, we want active customers. This will not be enough. Was okay? Thank you. More? I have one for Ferran. I'm sorry. We will not go out without a question. The thing is that if the results obtained in terms of performance, not distance, performance, can be extrapolated to any kind of medium voltage distribution grid.
Well, actually, The performance that we have shown is the result of many different tests in different types of line. Some of them were short distance underground, others were long distance overhead. Some of them had transitions between overhead and underground, impedance mismatches, interferences. So, of course, that there's always a physical limit. But I would say to a reasonable extent, we can say yes, because in fact, some of the, more than the distance and the bits per second, some of the characteristics that we have talked about today are rate adaptation, for example, or the ability to behave as relay stations. So that means you can build up a complete network, and if you're not successful at the first attempt, maybe you can ask another PLC to behave as a relay system and transmit and be able at the second, be successful at the second attempt. So I would say a reasonable yes. That's my feeling. There's always a physical limit, of course, and that seems to be around 8 kilometers. It is.
Yeah, 8 kilometers walking in Vallfogona is not that easy. I mean, question, I mean, for all about the batteries. This morning we had the Nissan people, and there's plenty of batteries. You know, I don't know if you're aware of a company in Valencia called Ampere. They are producing batteries. And this morning someone was talking about the business case of batteries of 5,000 euro and so on. What Ampere, they explain is that they are only selling batteries for home. I don't know if you have seen, they are round. They try to do something which is fancy that you can even decorate your house. The people which is buying batteries at that moment, what they say, is people that is not interested in making a business case, is interested in showing his batteries to the neighbors and friends. So there's no business model behind, which is great. Imagine buying something without paying attention to the cost or to the benefits. One more thing, just a comment. I have a Nissan Leaf, and when people know that you have an electric vehicle, they say, have you already calculated the savings and so on? And my question is, you have a petrol car, have you calculated it? I mean, how can I be the one having to explain why I'm doing such a thing? Yeah, the batteries. So we have batteries in the electrical world. I mean, they were not expected. They were expected only for the mobile devices. And then we are talking about forecasting and managing the electricity. And if I'm not wrong, in Germany, when you have a battery, they ask you if it is consumption or production, to apply some fees. I think that you have to define which kind, if you put which side are you placing your battery. So what do you think about the impact of the batteries in households and all this? It's an extra difficulty for forecasting?
Forecasting, that's me, yeah.
Yeah.
Well, I think in terms of forecasting, well, yes, because the behavior of the batteries is driven by the prices. So it's not the real demand, what you see, but it's in reaction to prices or autarky of a home. But I think it's the other way around, what Bernd asked, to the local markets. And I think maybe we are somewhere in the transition between a DNO to a DSO, distribution network operator to a system operator. And system, it means services, and one kind of services is being the enabler for a local market. And that means to provide something like a price signal. And if you give a household a price signal and say, okay, at the moment, by tariffs, for example, but not as fixed tariff, let's say from 8 to 20 hours a day it is this price, but something which you get as a forecast. Every day you get a price forecast. And when you have something automatically, that's very important, I think, something automatically that reacts to that. So a kind of demand response in a household. And then the battery is the enabler to take part on this market. And maybe in this case, it's also a question if the IDPR and all the concept has some add-ons, and I think it's for local markets. In terms of forecasting, yes, it makes things a little bit different. For example, we see it on the thermal side. If you talk about district heating, for example, it's not so easy to make a forecast like you do for power, but usually power is not start. So in the moment where you have a demand, you have a generation. So you really make the forecast of a demand. It's not the same on the heat side. You make a forecast of when it is generated, but not when it is consumed. So there's a storage between. So yes, forecast will be worse, let's say 2 or 3% worse when actually, but on the other side, it's the enabler for the local market.
Last question or one.
I would like to ask about the policies, maybe I guess for each speaker, of your field, what would be the main constraint to the technology, to get the most value of the technology in terms of what policy is constraining right now, and how these policies could be changed?
Who will start?
In Spain, we will need to change a lot of policies. But next September, we achieve our next new country in Europe, but we don't have problems. Let me say that in the beginning, believe me that the problem it was in several levels. We had the first goal to the first challenge to achieve. It was design, explain the needs. It was a large discussion about what is needed, understanding the real needs. Under the umbrella of the European Commission, this project, we are able to check everything of technology, exchanging relation, building between neighborhood and customers. The day after, when we conclude this project, is this year, July. I will like that the technology was working like now. We are creating island scenarios to work, but I don't know what is, something could be something you have best answer. What is the change of the relation between retailer and the customers using technology? For me, in this real project, is still operating and doing the same. The future changing the concept of the model of the markets. What changed? The legacy, the regulation, or that will give the flexibility to achieve relationship between producers, consumptions, neighborhood, because DSO, just we can share electrical infrastructure to get this transaction. But legal, we are installing the device, following the technical legal issues. This technology can still operate, because at least we increase the level of the intelligence for each one secondary substation. We are managed low voltage level in the electrical grid. It is possible. It's not out of legality in Spain. But to create an island with the safety rules is the same. A changing business case, this is a question from economical skills. I don't have a clear answer.
Me neither. So, no, you know, those are things that we can dream on. We can make business cases, PowerPoints, but at the end we will have the constraint of the regulation. No? In 3 or 4 weeks, we will issue a document which is called Policy Recommendations for regulatory bodies in Europe for the distribution of the future, because if regulation is not advancing a little bit, anything that we have in mind and we think it's logical and will service and will solution some of the issues which are coming, things will not happen. No? The devices in Vallfogona will keep up and running even after the project, but we can do it because we are small. I think nobody here will denounce us. And it's not visible. Let's say it's only visible for people that we invite to see it. We will probably keep it up and running just for other companies or universities or anyone willing to make tests and to learn from the experience over there. But it's not visible. I mean, this is something that if you made in the middle of the city, you are every day in the newspapers. And in fact, we are having problems because we are never in the newspapers. We would like to be a little bit more. But it will be up and running. But it's absolutely out of any kind of regulation. So now Ms. Assumpta Ferran, please, Assumpta, which is the Director of the Catalan. So you're ready? Yes, thank you. Oh, yes. She's the Director of the Catalan Energy Agency. And we are very lucky, the Catalans, because we have beach, we have mountains, we can ski, and we have her as Director of the Catalan Energy Agency because she has cleared the line. She's motivating electromobility. She's very strong on it. We have very good meetings, and the message is very clear. And especially, she has been supporting us from the very beginning. So thank you. And the floor is yours.
Gràcies, Santi. Good afternoon, and thanks, Santi, thanks, Estebanell, and CIPCEA, and all the other organizations that show us that the clean energy transition, it's not only possible, it's already here. Even if lots of people doesn't want to listen us. Even in this case, it's already here. Why I'm saying that most people doesn't listen us about the energy transition? For example, some of you has asked about policies. I don't know, it was already here, I think, you. Well, tomorrow starts in Madrid a great meeting with the Commissary of Energy and Climate Action, Miguel Arias Cañete, with our president, well, our president at this moment, Rajoy, two ministers, the one from energy, the other one from environment, and all of them, Catalonia, I don't know, but energy, it's not invited. Not only Catalonia, because ICAIN, the organization that I represent, it's also at this moment president of all the energy agencies in Spain, and it's not invited there anyway. So they are not, I don't know what they are going to talk about. But the meeting is about climate change and energy transition. I insist, the energy agencies won't be there. So I don't know what they are going to talk about. Probably they are not going to talk about smart rural grids. Probably they are not going to talk about this. I don't know if they are going to talk about smart grids. Maybe, but we don't know it. I suppose they will talk about energy, renewables energy, but it's a big concept. Well, we've been talking about this concept during 25 years, so it's new, it's not new. The problem is, are they going to talk about that none of this will be possible if we don't change a very big change of laws, fiscality, financing, all of this? This won't be possible, probably. But anyway, if they don't do it, we will do anyway the energy transition. Why? This is maybe the big question. Why we will do it anyway? I want to talk about the word prosperity. This morning when I was coming here on the radio, I hear Edmund Phelps. Edmund Phelps is a Nobel Prize in economics. And he was talking about a new book, which is mass prosperity. And he tells that prosperity, it's not only to earn more money, it's not only this. It's also something else, probably also something much more important, which is that it's something that it's, at this moment it's happening. And I think it's happening here in this theater, which is that most of people is flourishing. It's getting involved in something which is, which involves changing the world, changing things to make it better things. What is changing? What is these people involved in? Most of you are involved in this, in innovation. Which kind of innovation? In that innovation that it's, gave us the answer of most of the challenges. Climate change, air quality, security, all of the challenges are here. And most of people it's involving and trying to make an answer of these questions. So we are sure that it will happen because this is happening in all the world, not only in Germany, but it's clearly happening, or in Australia, or even in UK, of course in Norwegian. It's also happening here, with all the boundaries you can imagine, but it's also happening here. Why? Because, look, I think that one of the last questions was about batteries, which was the business model about batteries. Probably at this moment there is not business model. We are building the business model at this moment, but we are not only building this business model. Now we have technologies. All day you've been talking about smart grids. We've been talking about a lot of physics, telecos, but also specific technology. Electric car, solar PV, batteries, all of them with digitalization of energy, it's equal to services. What kind of services? We will see what kind of services. But at this moment, we already know one of them, some of them. For example, storage services. In California are already starting these services. Solar services, we know Solar City, now Tesla, it's a solar service. We are seeing these kind of business models. Electric mobility services, of course, they are already here. We know them. For example, Madrid, we have two companies, eMove and Car2Go. They are already working in it. Autonomous cars, I can imagine autonomous cars with polluting cars. I'm sure that they will be electric cars. Such services, I think that all of us are completely agreed that they are new business models. So the energy transition will be here because even some policies doesn't want them. What is completely true is that disruption energy, it's here. Santi always says, you say this, but things are not happening. Yes, if we go to Granollers, Barcelona, it doesn't matter, we can see energy, solar roof technologies or electric cars. Yes, we don't see it at this moment, but we will see them. I'm sure we will see them. Because these new business model services, it's what make society flourish again, and we need it. We need it. It's not only just to talk about climate change, it's about to talk new business models, new energy, and a better world. That is. About ICAIN, we are not really agency at this moment. We are an institute. We are an energy institute of energy. What we are trying to do, we are a little ones. We are not a very big organization. But we are focusing in those aspects that we are sure that will be important to change things. For example, at this moment we have present and the government has approved the national agreement on clean energy transition. This is a big agreement, but there is a picture in this agreement. There's a picture where there is building, there is an electric car, there is a solar PV, and there is also an electric grid bidirectional. This is in the same picture. This is energy transitions. We can discuss about renewables. We can discuss about what you want, but The energy transition is the democratics of energy. So this is the picture. And we are sure that this is what we have to boost in order to change things. So where we are working in electric car, of course, but we are little, I tell you. We cannot boost electric cars just in it. What we can do is to improve the charging, the charging infrastructure. Yes, we can do this because it's not really very expensive if we do it together with the municipalities, and it's what we are doing. In fact, at this moment, if we had a little bit more money, because we had no, but next year will be already done it, we will have fast electric infrastructure every 50 kilometers, more or less. This will be at the end of next year. So it's already here. Fast charging, that means 50 kilowatts. And I insist, if we could have only 2 million euros, just only 2 million euros, at the end of this year, all Catalonia will be covered with fast charging. That's what it means. So it's not really expensive. It's to believe in it and doing, because it's not a problem of money, because it's not really expensive. It's a problem of lawyers. It's a problem of know what you want to do, and it's a problem of culture, of course, because when you say people, we will have more or less 100 of fast charging points in strategic points of Catalonia. People say only 100. We have 1,400 petrol stations. It has nothing to do. We don't need this. This is another model. It's like, I always say, it's like when Henry Ford, 120 years before, people asked them for horses, for more strong horses. They don't ask for petrol stations. They didn't know what was a petrol station by that time. Now it's exactly the same. But we are already there. What we are boosting? Batteries. How? Someone asked about the price of batteries. Yes, they are still expensive. They are going fast, cheaper, but they are still expensive. But we know that we won't have solar roof installations if we don't have batteries. Why not? Because our law says that you cannot share energy at this moment. For example, all of this is a pilot project because all of these houses cannot share energy. Because it's pilot, yes, but they couldn't. So what happens if you live in a country that it's sunny, it's very sunny, like us, but you are not at home when your solar roof is producing electricity? You cannot share it, you cannot sell to the company. What happens? No one's have solar roof installations, unless if you have a battery. And you can store it and you can use it when you go home. So it's what we are doing. We are subsidizing batteries. How much of the cost of the battery? 70%. Batteries for households. That means that the capacity has to be less than 20 kilowatts per hour. 70%, the maximum of 5,000 euros. That's what we are trying to do. It won't be easy, even with this subsidy, because most of people doesn't know that they can do it. In fact, most of them think that this is forbidden. And even if they know that it's not forbidden, it's completely difficult to obtain all the permits you need, most of them from the company. So most of them are different. Stevenage is different, Bassols is different, but still we need lots of documents and permits to do it. And most of municipalities has complicated laws to use the roof to put solar installations. So we have to change lots of things. But by the beginning, we start with batteries. Why? Because most of people, and they are not rich people, live in a house. And not because they are rich, because they live in a little municipality. Our minister says because they are rich. Well, they are not rich. So we want to start with them. We want to start with them because there is something else. Someone has asked about sharing mobility. Yes, in Barcelona, it's possible to share mobility, but if you live maybe in Espluga de Francolí, where I live, this is a village of 3,000 people, it's quite difficult to share your car. That means that people needs the car, much more than ones that live in the city. In fact, during the week I live in Barcelona, and I never use my car, never. I go by bicycle, it's fantastic. But on the village, you need the car. So if you live in a village, you live in a house, and you need the car, you have already a battery. Why not to start there? So we have to start with pilot projects, not only in a very rural villages. This is not really a village. By Fogona del Ripollès, yes, it's a village, but these are disseminated houses. We need to start in a region, in a normal region, not like Barcelona, but in a normal region. And just to implement all of this and to show that all of this is completely possible. Even laws, even fiscality, even financial tools that are not prepared for this energy model. They are not prepared at all. Our financial system is prepared to invest in very big projects, not in solar roof projects. So we need to change all of these things. But this is transition, and probably to change all of this is what makes flourishing lots of people and makes prosperity. Not because earning money. It's not necessary to have at this moment the business model. It's not necessary at this moment. What is necessary is to have the view that this will happen if we do it. And what is we try to do from the Energy Catalan Institute, which is a very little one instrument of the government, but it's full of people who want to make the energy transition. So I'm sure that we will do it, because to be difficult, it's a good thing for our brain. So let's do it, because it's possible. You show it's completely possible. It won't be easy. It doesn't matter. The challenge, it's even better. So let's do it. And just nothing else, thanks for the physics class. It was, I was thinking about it was 20 years ago without having a physics class. I'm physics, but it was 20 years ago without having a physics class. So it's a long time. So thank you very much to remember my last, when I was young. So thanks at all, and good luck, everybody, with this magnificent job that you are doing.
You see, she speaks about energy, she speaks about difficulties, and she smiles. So we are so lucky. So that's all. Thank you very much. It has been really, for us, has been a celebration. We still have to deliver the final results to the Commission, but that's peanuts for us. So thank you. We have some coffee there if someone wants to stay for a while and have a last talk with us. And thank you for coming, and enjoy the rest of the day, and have a good luck. Thank you.